definition of a derivative. So we have this graph here. Then let's say that we're going to have another x value over here, okay? And what this is going to be is this is going to be c plus some change in x, okay? So we have this second c value. We know it's different from the first c value that we have, okay? And so to get that, we've added some number to that. It's some number bigger than c, okay? Does everybody understand that concept, what the change in x is? Okay, so that would make, if we had another point up here, that would make its y value f of c plus delta x. And remember, delta x is just some change in x. All right, so then we have a curve. Okay, so just some curve there. And we're going to draw a secant line through these 2 points. And a secant line is just some line that's touching both points, right? Okay, so if we're looking at what this point up here would be, okay, so this point is going to be the point, it's going to have this x value of c plus delta x, and then it has a y value of f of c plus delta x. Now, what do we remember about slope? I'm trying to calculate the slope of something. Rise over run, right? Okay. So if I'm thinking about rise over run, and I'm going to apply just those Algebra 1 definitions of slope to this, and I want to find the slope of that secant line, okay? So we could use that same concept, rise over run, okay? So if I think about the rise here between these 2 points, that's going to be this distance here between these 2 points, okay? How could I find that distance? Subtract the 2, okay? So subtract the 2, what? The y values, right? Okay? So if I know f of c plus delta x is that whole distance, and then I know f of c is that gap that I want to get rid of, if I subtract the 2, then I'm going to get that distance here. So we can do f of c plus delta x, and we can subtract f of c from that, and that's going to give us that rise that we have in our problem. How do I get this run? Okay, and when I do the difference between the 2 x points, what happens? If I do c plus delta x minus c, we just get the change in x, right? Okay, so that change in x was just that change between my 2 x values there. Okay, so when we're figuring out this definition, okay, we want to say the slope of the secant line here. So remember, we always use m for slope. So the slope of our secant line would be rise over run And in this case, our rise is f of c plus delta x minus f of c. And our run is delta x. And I guess we could make ourselves a note that this delta x came from doing c plus delta x minus c. Okay, so just so there's no confusion about where that came from later on. It all comes from this rise over run definition. Okay, so what we have here is actually going to end up being the definition of a tangent line that we're going to use. Okay, and to make it the definition of a tangent line, what's the difference between a secant line and a tangent line? Okay, so a tangent we're going to want to only cross at one point. Okay, and so if we look at this kind of diagram, this will help us visualize this. Okay, so over here is kind of the situation that we have. We have these 2 points, they're far apart, okay? And we've drawn that secant line between them, okay? But if I watch, as I make that change in x smaller, what happens to the points over time? They're getting closer together, right? And so eventually, as that change of x is going to 0, we're going to end up getting our tangent line. Okay, so we're making our delta x arbitrarily small. The smaller we get, the closer we're getting to our tangent line. Okay, so if we take that definition that we just made for that secant line, and we say, okay, we want the limit as delta x is approaching 0, then we can get what our tangent line would be, the slope of our tangent line at that specific point. Okay, and what the tangent line is going to do, that slope of that tangent line, that is going to be what we're doing when we calculate derivatives. Okay? So anytime you hear the word derivative, taking the derivative, what that means is we're finding the slope of that tangent line at that specific point. Okay? So that's why it's kind of important to go through this definition. Is if I just threw out the word derivative and we just started using the shortcuts, we're like, where does this come from? What are we even calculating? Okay, but this is what we're calculating. Is we're calculating that instantaneous rate of change at that specific point. Okay. Does this visual make sense? Does that help us kind of understand how we're getting the tangent line definition there? Okay, so, and I'm going to take these notes and I'll make a PDF of them and I'll upload it for you guys. Okay, so then our definition of tangent line for our derivative. Okay, so formal definition here is going to be the limit as delta x approaches 0 of the change of y over the change in x, which is going to be f of c plus delta x minus f of c over delta x. Okay, so this is the definition when x is c. Right, we've made x be sub c. All right. So the definition that we're mostly going to use is going to be this one, and it's just the same thing. We're just going to change a few things and make it a little bit easier. Okay, so we're going to say the limit as h approaches 0 of f of x plus h minus f of x over h. Okay, and all we've done here is just for the purposes of not having to write delta x a bunch of times, we've replace delta x with h. So in this case, delta x is h. You can use delta x, like you can use the same formula and you can write the limit as delta x approaches 0 of f of delta x plus h minus f of x over h, over delta x. But when you use h, it's just one less thing to write. And these are already very heavy in writing when it comes to doing these problems. So leave yourself some space when you're doing your homework. All right, so let's do an example with this. Okay, so example 1. Okay, so we're going to find the derivative of this function. Okay, so sometimes they'll ask you just to find the derivative of the function. Sometimes they'll ask you to find it at a specific point. It's the same process. What we're going to do here is we're going to find an actual equation, so an expression, that if we wanted to find it at a specific point, we could just plug whatever x value into it, and it would give us the derivative at that specific point. Okay, so it's giving us more of this generic formula that we can use to find any point, any tangent point for that graph. But if they went ahead and gave you the point, then you could plug the point in earlier and make it a little bit easier. Okay, so what we're going to do, so one thing in this class, we're going to use this notation for derivatives sometimes. So this is f prime of x. We're going to say the limit as h approaches 0. Okay, and so we're going to use our definition. So if we're doing f of x plus h, so this is composition functions. So we're going to take x plus h, and we're going to put it where x is in our function. So we have that x cubed plus 2x. So we're going to replace it with x plus h cubed plus 2 times x plus h. Everybody understand that part so far? Okay, so you're taking that x plus h, plugging it in for x. Then it's minus f of x. So it's minus just whatever the function is. X cubed plus 2x. All over h. Okay, so this is where the algebra gets a little lengthy. So when we do x plus h times x plus h, what are we going to get? So x squared plus 2xh plus h squared. Okay? And we're going to multiply that by x plus h. So kind of think of whatever way that you want to do it. If you want to take the first term and multiply it by everything in the next parenthesis, or if you want to do each term in the first parenthesis and multiply it by the first term, whatever you want to do for that. Okay, but let's do, so x squared times x is going to be x cubed. X squared times h is hx squared. Then we can move to the second term, 2xh, so 2x squared h plus 2xh squared. And then we'll have plus x h squared plus Okay, this one is very important to keep your limit symbols throughout it. I am gonna get tougher in like the nitpickiness of stuff like that, because you'll lose points if you don't do it correctly. All right, so we have x cubed have some like terms. So we could say plus 3hx squared plus 3xh squared plus h cubed. Okay, and then we have to deal with the rest of that problem as well. So don't just cube that and then put it there and forget about the rest of the problem. Okay, it was 2 times x plus h. So that's going to be plus 2x plus 2h. And then we got to distribute the negative x cubed minus 2x. Yep. So like I said, this is going to be a little algebra heavy. And most people understand the process of this. They just make small mistakes. Okay, so we have some canceling we can do. We have x cubed minus x cubed, 2x and 2x here. So 3hx squared plus 3xh squared plus h cubed plus 2h. Now, what's preventing us from being able to just plug 0 in is that h on the bottom, right? So is there something that I could do to this to manipulate it where I could cancel the h on the bottom? Okay, so I can factor an h out of the top. And you're going to notice a pattern that this is going to happen every time with this limit definition. You have that h on the bottom. You're trying to get rid of h. So stuff should cancel, and you should be able to factor h out, cancel it, and then go on from there. So we have 3x squared plus 3xh plus h squared plus 2. So h's will cancel. We have 3x squared plus 3xh plus h squared plus 2. So when we plug 0 in, what happens to the middle two terms? They're going to go to 0, so they're not going to really exist anymore. So we're going to be left with 3x squared plus 2. Okay, so what is that? It's the derivative. And so what does that give us? What could we find out with this?
Slope.
Okay, so the slope of, so not the tangent line to the curve, right? Okay, so the whole purpose of this is now we have this equation. So let's say I want to know what the slope of the tangent line is at x equals 2. I can now take 2 and I can plug it in here. And I can say, okay, the slope of the tangent line at x equals 2 is 14. So for a while, we're just going to be figuring out how do we even do derivatives. Then we're going to use them more practically in some word problems. They're going to help us with some like rate problems and some different things like that. So they're very useful in certain contexts. And then, so we're going to do derivatives. We're going to talk about this definition. We need to practice this definition and be able to use it. Then we'll go into the different shortcuts. There's some different rules that we'll learn. So there's power rule, quotient rule, and some others that I can't remember currently, but I will remember. But it's my day. So there's several rules that we'll go over, and then we'll go into integrals. And an integral is actually kind of like it undoes a derivative, so kind of the opposite of deriving is taking the integral. And that's talking about some area under the curve type stuff. And then we'll use these kind of in different word problems. But right now,